Okay, good afternoon, everybody. I'm Jian Li. This is a joint work with Li Jiechen and Mingda Qiao. Both are undergraduate students. So we are all from Tsinghua University. So we studied this very classical best arm identification problem. So in this model, we have a set of n arms, and each arm is associated with a reward distribution with unknown mean, which we term as theta I. And we can adaptively pool those arms, and upon each pool, we get a reward sampled IID from the corresponding reward distribution. And our goal is to identify the best arm using as few samples as possible. By best arm, I mean the arm with the largest mean. So here in this talk, we assume that when we are talking about the upper bound, we assume all the arms are one sub-Gaussian. And when I talk about lower bounds, we assume all the arms are Gaussian with unit variance, of course, with unknown means. Okay, so the best arm identification has important applications in clinical trials, and it has many extensions. For example, instead of choosing the best one arm, we can choose the best k arms, or we can even have a combinatorial constraint defined over the arms, and we want to choose a best subset. And they have applications, a variety of applications, for example, in cross-sourcing, online advertisement, and reinforcement learning. Of course, to understand those extensions, it's better to have a complete understanding of the best arm identification problem. So let's start with a simple case where we only have two arms. Suppose we have just two simple coins. One is a fair coin, and one is slightly biased. Suppose we know that the gaps of their mean, let's denote this gap by the big delta. And it's easy to know that it's well known that we need this delta to the power of -2 log small delta to the -1 samples by simple Chernoff bound. And the lower bound is also easy to prove. There are a couple of different ways to prove it. And this is based on we know this big delta. We know the gaps. So if the gap is not known, actually, so the bound becomes a little bit more interesting, and there's an additional log-log term. And this is actually, we can easily find the algorithm which based on guess and verify. We guess the gaps by exponential decreasing sequence, and we verify each our guess. And this log-log term is due to the union bound over all the iterations. And it's also possible to prove that this bound is also necessary, and this is proved by Farrell in 1960s. And the underlying reason is actually based on the law of iterative logarithms, where this log-log come from. Okay, so let's come back to the more general problem. We have n arms, and we want to find the best arm. And this problem was formulated very early in the 1950s. And let's define the gaps of arm I to be the difference of the best arm, the mean of the largest mean, and the mean of the ith arm. And let's review some classical results on this problem. So first, minutia cyclists provide a lower bound, which is a summation of all the gaps to the -2 and log small delta to the -1. So actually this lower bound is an instance-wise lower bound, meaning that for every instance, it requires this many samples, no matter what your algorithm you use. Okay, and later on this problem has been studied extensively, and there are many upper bounds, or at least these are upper bounds. And prior to our work, the best bound was obtained by Carning and independently by Jimis using different techniques. And let's look at their bound. So this part is actually the same as minutia cyclists lower bound. And this part, you can see this is an additional log-log term. And let's compare with this. This is a minutia cyclists lower bound, which is the same as the first part. And for the second part, actually, we can recall the Farrell's lower bound. There's additional log-log term. Therefore, it's very tempting to believe that this bound is already optimal. But actually, of course, if you want to formally prove that this is optimal, you have to prove a corresponding lower bound, which is a summation of delta -2 log delta -1, right? So initially, this is what we initially try to prove. And as we prove it, it turns out this is actually impossible, because actually we found a better algorithm that can perform strictly better than this upper bound, meaning that this is not optimal. And actually, so this is so in a previous version of this COLT paper, we gave proposed this gap entropy conjecture, which also appears in the last year COLT open problem session. So let me tell you what is this conjecture, which states what should be the instance sample complexity for best arm identification problem. Let's look at this x-axis. So we divided this x-axis using exponential e to the minus 1, e to the minus 2. This we call each interval bucket. And each green point represents an arm with gaps lying in this bucket. For example, this represents an arm with gaps between e to the minus 2 and e to the minus 3. Okay, all they present. Okay, so now let's compute the complexity for each bucket. So the complexity of the bucket I is just the summation of all the arms in this bucket and the delta minus 2. Okay, so we term this as the complexity term of the ith bucket. And then we normalize this complexity term, normalize it so that this defines a distribution. And now we look at the entropy of this distribution. And we conjecture that the instance-wise lower bound of this problem is actually this quantity. The first hi is just the summation of their gap. And so this is the first part is just the multicyclic lower bound. And second part is new, and this is related to the entropy term. Okay. And actually, we also conjecture that should be a corresponding algorithm that can achieve this lower bound plus the two-arm bound. So this is optimal for two arms. And actually, this is a little subtlety. Please come to that poster. And actually, this gap entropy, we can prove that. So this gap entropy term is strictly better, is not worse than the Carney's lower bound, and sometimes it can be much, much better. For example, if all the arms are located in one bucket, the entropy is much smaller. Okay, so this is our new bound. Actually, we prove a new lower bound. That is, this is the same as our conjecture bound, but we have some mild technical conditions. And we also have a new upper bound that is also the same as a conjecture bound, but with an additional term that is has a polylog factor. Okay, so I don't think I have times for the technique, but it's roughly based on elimination, and further refinement of Carney's technique, and we introduce a bunch of new techniques to deal with it. But unfortunately, the actual algorithm and analysis is quite complicated, and we hope that this can be simplified. And so if you want to know the details, please come to the poster session. Okay?